Hi class, welcome to lesson 57. By the end of this video, you should be able to use oxidation numbers to determine if substances are reducing or oxidizing, use oxidation numbers to determine if electrons are lost or gained by a substance, and to write the half reactions for oxidation and reduction. Let's go. There are lots of different types of redox reactions that happen in nature. In addition to simple cellular respiration, which keeps us alive, we can see redox reactions when fireflies glow to attract a mate, when anglerfish emit light to attract prey, and during the bioluminescence of various squid, jellyfish, bacteria, and shrimp. So in this reaction, you can see that we are given the oxidation numbers of many of the species. If no oxidation number is given and the species is by itself, it is behaving as a neutral atom, so its oxidation state is 0. So when we look for the oxidation, we want to find the species whose oxidation number increases. So what we see is zinc is changing from 0 to positive 2, and hydrogen is changing from positive 1 to 0. So in this case, zinc is undergoing oxidation because it is increasing in charge. Now the reverse is also true for hydrogen. Hydrogen's oxidation number is changing from +1 to 0. Its oxidation number is being reduced. So here in these species, you can see that the zinc is oxidized and the hydrogen is reduced. When we refer to what species is oxidized or reduced, we'll want to make sure that we include the oxidation number or the charge on the reactant side. So notice that it's H+ that's undergoing reduction, not simply an H. Now, let's take a minute to see if we can use oxidation numbers to identify the species oxidized and the species reduced here.
What I can do is I'm going to use my periodic table to do that. What I see is I have lithium. Now, lithium could have an oxidation state of +1, but here lithium is unbonded. It's a neutral atom, so it has an oxidation number of 0. Sodium in a bond always has an oxidation state of +1 and fluorine -1. But again, we have sodium here. Sodium's by itself, it's a neutral atom with 0. So if we continue to use our reference table, we can see the oxidation number of all of the species that are participating in this reaction. The next thing we're going to do is we're going to see how the oxidation numbers have changed. So what I can see is that the lithium has changed from 0 to +1, while the sodium has changed from +1 to 0, and the fluorine has stayed constant at -1. So after we assign the oxidation numbers, what I'm looking for is the reduction. Whose oxidation number went down? So here I can see the sodium ion was reduced, the lithium atom was oxidized, and the fluorine is unchanged. We'll call that the spectator. So it's important that fluorine is there so that the electrons can be transferred, but it's not actually changing in this reaction. Let's see if we can continue on with the next examples. Again, in order to find the oxidation numbers, you should use your periodic table of elements. But what you want to do is look for free elements. So you know their oxidation state is always 0 when they're unbonded. Now, I'm just going to go in and write the oxidation numbers for my bonded elements. And now let's do some bookkeeping. So here we can see that the potassium ion went from +1 to 0, while the lithium atom atom went from 0 to positive 1, and in this case, the oxygen remained negative 2. So we're looking for the species that is undergoing reduction. That is a decrease. So in this case, our potassium is reduced. Our lithium atom is oxidized because it's not reduced. Its oxidation number increases from 0 to 1. And the oxygen is the spectator. Here we have a synthesis reaction. We are synthesizing sodium chloride. We see that the sodium atom is changing oxidation state from 0 to positive 1. The change from 0 to positive 1 is an increase, so that is oxidation. The chlorine is changing from 0 to negative 1. That's a decrease, so that's the reduction. There is no spectator in this reaction. Please pause the video and try in the last reaction if you can identify the species oxidized and the species reduced. You'll find the answer at the end of the video.
Here we have 4 different chemical reactions. What we'll have to do to see if they are actually redox reactions is assign all the oxidation numbers and see if they are changing throughout the reaction.
So here in this example, we are asked, are these all redox? So the first step will be to use your periodic table, just like in the last example, and assign oxidation numbers for each element. Hold on, let me do that and I'll be right back. Okay, so now that I went and I assigned my oxidation numbers, I just have to see if they change. So in the first reaction, you can see that the oxidation number of oxygen is changing. So is this redox? This decomposition is redox, as are almost all decompositions. Here we have a synthesis reaction. We can see that lithium is changing from 0 to positive 1. So is this redox? Yes. In this reaction, we have single replacement. Notice that magnesium's oxidation number is changing from 0 to positive 2. So is this redox? Yes. Now in all of these 3 reactions, I identified redox by only seeing one change in oxidation number. Remember that in redox, there will always be 2 changes in oxidation number. So in the first reaction, oxygen's oxidation number goes up while chlorine's oxidation number goes down. Or in this synthesis reaction, lithium's oxidation number goes up and fluorine's goes down. In the single replacement reaction, magnesium's oxidation number increases while hydrogen's oxidation number decreases. Now this last reaction, a double replacement reaction, when we look at the species and we compare the oxidation numbers on both sides, sodium stays at positive 1, oxygen stays at negative 2, hydrogen stays at positive 1, lithium stays at positive 1, and bromine stays at negative 1. So this is not a redox reaction, and double replacement reactions are never redox reactions.
Now recall that we use reference table J to figure out if a redox reaction will be spontaneous. The species that is more active replaces a species that is less active in a single replacement reaction.
So what we'll do is we look for the single element to see if it is more active than the paired element that it desires to replace in order to obtain a lower energy, more stable, noble gas valence electron configuration. So what we notice here is we look for lithium, which is the very top of the table. So since lithium is the most active element, it will definitely undergo a spontaneous reaction. So yes, this will be spontaneous, which means this is exothermic. The potential energy diagram for this reaction will look like this, and energy will be written as a product. Next step, we have copper. Here's copper. When I look at copper on my reference table, I can see it's down here. Copper, I'm going to have to compare with hydrogen because you cannot compare items in different columns. So copper is less active than hydrogen, so this reaction will not be spontaneous. This reaction is endothermic, meaning it has a potential energy diagram like this, and we'll have to write energy as a reactant here. Now please pause the video and try the last two examples to figure out if they are spontaneous or not using reference table J. The first step in writing half reactions is to assign the oxidation numbers for each of the species. So let's assign the oxidation numbers for each species in the decomposition of zinc sulfide. So a half reaction shows you half of exactly what is happening. It will show either just the oxidation, which is the loss of electrons, or just the reduction, which is the gain of electrons. So recall that you're going to use a periodic table to look up the oxidation numbers of the elements. So here zinc is changing from a compound to a lone element. So its oxidation number is changing from +2 to 0. This is a reduction of charge. So zinc is undergoing reduction. Sulfur's charge is changing from -2 to 0. So it is undergoing an oxidation or an increase in charge. Notice that for all reactions, including redox, matter must always be conserved. We show the law of conservation of matter or mass by using coefficients to balance a chemical reaction. So what we notice is, as zinc's oxidation number decreases, we must be gaining 2 electrons. And while sulfur's oxidation number is increasing, this must occur because we are losing 2 negative electrons. So in the reduction half reaction, we're only going to represent the gain of electrons, so we're only going to show the reaction involving zinc. Notice that in this reaction, we must make sure that the gained electrons are reactants that come before the arrow, and the total charge before the arrow must equal the total charge after the arrow, or in other words, charge is conserved. For the oxidation half reaction, we look at the reaction for the loss of electrons, which happens with sulfur. And again, we have to make sure that electrons lost are products that fall after the arrow and that our total charge is conserved. So when writing half reactions, the reduction always shows the gain of electrons, and the oxidation half reaction always shows the LEO, or the loss of electrons. But like in all systems, there must be a conservation of charge. The number of electrons gained must equal the number of electrons lost. So when given a reaction, we have to evaluate what's going on. So here, our tin's oxidation number is changing from 0 to +2. That is an increase. That means that this half reaction is an oxidation. During oxidation, electrons are lost. Notice that electrons are after the arrow or on the product side of the reaction. Here, copper ion is changing from +1 to 0. +1 to 0 is a decrease or a reduction in number. So this is a reduction. Notice that during reduction, electrons are gained. Electrons that are gained are on the reactant side or before the arrow. Let's look at these two other equations. Notice they both have some missing information. But looking at the oxidation numbers, I can see that when I go from 2 to 0, that is a reduction in number. So this mercury is undergoing a reduction. We see that positive 2 plus some amount of electrons should equal 0. If I add 2 negative electrons, then positive 2 plus 2 negatives equals 0. Let's look at the gold here. Notice that gold is changing charge from 0 to positive 3. That is an increase or an oxidation. When the gold atom undergoes oxidation, it must lose electrons. How many electrons? Well, we need to balance the charge. So 0 equals 3 plus 3 electrons. Now my charge is balanced.
One thing to know about redox is not only do we have the species that's oxidized or reduced, but there's another terminology called the agent. So the species that is oxidized is sometimes referred to as the reducing agent, and the species is reduced is sometimes referred to as the oxidizing agent, because these items cause the reverse process.
Let's look at this final example here and see if we can identify the species oxidized and the species reduced. In order to do so, we'll have to assign oxidation numbers. So lithium here, we can see element number 3 is always a +1 in a bond. But chlorine, element number 17, has many oxidation states. So in order to figure it out, we have to look at the next element, oxygen, which is always -2 in a bond. So what we know is the total charge of this must be 0. So if we have +1 from the lithium and a total of -6 from the oxygen, the chlorine has to be +5. As we continue on, we're going to do the same thing with the new compound formed from this decomposition. So lithium again is +1 and oxygen is -2. Now in this compound, chlorine must be +1. And here we have oxygen all by itself. It has no partners, so it is an oxidation state of 0. So what we can see is that the lithium stays +1 the entire time, making it the spectator. The chlorine changes from a +5 to a +1. When you go from +5 to +1, that is a reduction in charge. And the oxygen changes from -2 to 0. So this is actually an increase in charge as I'm becoming less negative. So the oxygen undergoes oxidation. Here, we need to compare the lone element magnesium with the paired element calcium. So here we find magnesium, and magnesium is less active than calcium. So this reaction, again, will not be spontaneous, and instead, it is endothermic, meaning you must add energy for it to happen. And finally, we're looking at this reaction. This is the reaction we used in lab to produce hydrogen gas, that fun, explosive, flammable gas. So here we're going to compare zinc with hydrogen. So here, what you can see is that hydrogen is here and zinc is above it. So zinc is more active than hydrogen. So this reaction happens spontaneously. All we had to do is mix the chemicals in lab and we had a chemical reaction. So it is exothermic.